Welcome to ProximaCentauriB. You're passionate about space, exploration, and the mysteries of the universe. You're in the right place. Join me on this incredible journey as we dive deep into the cosmos, uncovering secrets of the stars, planets, and everything in between. Don't forget to like, subscribe, and hit the bell icon so you never miss an adventure. Let's explore the universe together. Look up at the stars and not down at your feet. The words of Stephen Hawking echo as we gaze into the endless night sky, a canvas dotted with infinite possibilities. For as long as humanity has existed, we've sought meaning in the stars, a dream that transcends time, borders, and cultures. Imagine standing on Earth, looking toward Proxima CentauriB, a planet orbiting our nearest stellar neighbor, Proxima Centauri. This small, rocky world exists 4.24 light-years away, an almost incomprehensible distance. Yet, it beckons us like a far-off lighthouse, calling sailors lost at sea. What lies beyond the edge of our cosmic shoreline? Could Proxima Centauri be humanity's second home, a refuge for our species to flourish among the stars? These questions ignite a fire in the hearts of scientists, dreamers, and explorers alike. In this script, we embark on a journey to explore these possibilities, blending cutting-edge science, philosophical musings, and the raw power of imagination. Through this lens, Proxima Centauri transforms from a distant speck into a symbol of humanity's potential. Proxima Centauri represents more than just another exoplanet. It orbits within its star's habitable zone, a region where conditions might allow liquid water to exist, an essential ingredient for life as we know it. Astronomers discovered this world in 2016 using the radial velocity method, which detects the gravitational tug of a planet on its star. This monumental discovery solidified the notion that Earth-like planets might not be unique. Proxima Centauri has become the focal point for interstellar dreams because of its relative proximity. At 4.24 light-years, it's closer than any other potentially habitable exoplanet. However, even this close neighbor lies at a distance that current technology struggles to fathom. Let us step back and consider the broader picture. For centuries, we've explored the limits of our world, from traversing oceans to scaling Everest. Space exploration is a natural extension of this indomitable spirit. The 20th century witnessed humanity's first small steps into the cosmos. From Yuri Gagarin becoming the first human in orbit to the Apollo astronauts walking on the moon, these achievements have paved the way for far greater aspirations. Proxima Centauri is our next challenge. It embodies our capacity to dream big and to dare greatly. What we achieve in the pursuit of this goal will not only redefine what is possible, but also cement humanity's legacy as a species that refused to be confined. Today, Earth faces numerous challenges: climate change, overpopulation, resource depletion. Proxima Centauri offers a glimmer of hope, the possibility of a second home where humanity might not only survive but thrive. While such a venture may be centuries away, the vision itself serves as a unifying force for innovation and progress. In the pages that follow, we'll delve into humanity's storied history of space exploration, the science behind exoplanets like Proxima CentauriB, and the challenges of interstellar travel. We'll also explore the advanced technologies that could one day take us to the stars and reflect on what it means to be explorers in a vast and mysterious universe. Our journey begins here, with a simple yet profound truth. Humanity has always reached for the stars, and the stars have always reached back. Proxima Centauri is not just a distant world, it is a mirror, reflecting our aspirations and our resolve. What if we are meant to explore, to journey beyond the confines of Earth? This is the question that will guide us through the next steps of this exploration. Humanity's first steps into the cosmos for millennia, the stars have captivated human imagination. Ancient civilizations wove myths and stories into constellations, interpreting the heavens as a map of the divine. However, it wasn't until the mid-20th century that humanity moved from gazing at the stars to reaching for them. In 1957, the Soviet Union launched Sputnik 1, a small metal sphere, into orbit. This simple act ignited the space race, an era of unprecedented innovation. Less than 4 years later, Yuri Gagarin became the first human to leave Earth, orbiting our planet aboard Vostok 1. His journey marked a monumental shift. Humans had become a spacefaring species. On July 20, 1969, Neil Armstrong and Buzz Aldrin stepped onto the lunar surface, etching their names into history with the immortal words, "That's one small step for man, one giant leap for mankind." The Apollo program symbolized what humanity could achieve when driven by curiosity and determination. The moon landing was more than a scientific triumph, it was a statement of possibility. If humans could travel 384,000 kilometers to the moon, what else might we accomplish? Could we one day reach distant stars? The 1970s ushered in another milestone with the launch of the Voyager probes. These twin spacecraft, designed to study the outer planets, have since become humanity's emissaries to the cosmos. Carrying the golden record, a time capsule of Earth's culture and biology, the Voyagers remind us that exploration is not just about science, it's about storytelling. Voyager 1, now the farthest human-made object from Earth, continues its journey into interstellar space. Its mission embodies humanity's insatiable curiosity and its desire to connect with the unknown. For centuries, philosophers and scientists debated whether planets beyond our solar system existed. The search for exoplanets began in earnest in the late 20th century, fueled by advancements in telescopes and detection methods. In 1995, the first confirmed exoplanet orbiting a Sun-like star, 51 Pegasi, was discovered using the radial velocity method. This revelation transformed our understanding of the universe. Suddenly, the idea of Earth-like worlds became not just plausible but probable. In the decades since, missions like Kepler and TESS have catalogued thousands of exoplanets, many within their stars' habitable zones. Among them, Proxima Centauri stands out as a prime candidate for exploration, sparking dreams of interstellar travel. The journey to Proxima Centauri will build on a foundation of technological breakthroughs. Each achievement has brought us closer to the stars. From the development of liquid-fueled rockets by pioneers like Robert Goddard to the Saturn V's unparalleled power, advancements in rocketry have been the backbone of space exploration. Ace stations and long-duration missions. The International Space Station, ISS, has taught us how to live and work in space through extended periods. Lessons from the ISS will be critical in addressing the challenges of interstellar travel. Robotic missions to Mars, Jupiter, and beyond have expanded our knowledge of the solar system. They've also demonstrated the feasibility of autonomous systems, essential for interstellar probes. In the 21st century, humanity has shifted its focus toward Mars as the next frontier. SpaceX's ambitious plans for a Mars colony highlight our growing confidence in venturing farther from Earth. Yet, even as we dream of Martian settlements, our gaze often drifts to the stars. Proxima Centauri represents the ultimate challenge. While Mars is a stepping stone, interstellar travel is the destination, a goal that will require us to rethink not just technology, but the very nature of exploration. Throughout history, dreamers and visionaries have pushed humanity toward the stars. From Konstantin Tsiolkovsky's theoretical work on spaceflight to Carl Sagan's poetic vision of a connected cosmos, these individuals have inspired generations. Elon Musk, Jeff Bezos, and others are modern heirs to this tradition. Their initiatives aim to make space travel routine, creating the infrastructure needed for even grander endeavors. Yet, it is not just scientists and entrepreneurs who drive this dream. Artists, writers, and filmmakers have long imagined interstellar voyages, from Jules Verne's From the Earth to the Moon to Christopher Nolan's Interstellar. Fiction has a unique power to ignite imagination, turning abstract ideas into tangible possibilities. Each milestone in space exploration has been a stepping stone toward a larger goal. Sputnik, Apollo, and Voyager were not ends in themselves, but parts of a continuum, a journey that began with curiosity and will one day culminate in humanity's reach for other stars. Proxima Centauri is the logical next step in this progression. It challenges us to think beyond the familiar, to confront the vastness of space, not with fear, but with resolve. Humanity's journey to the stars is rooted in a rich history of exploration and discovery. From the first tentative steps into orbit to the bold aspirations of today, we are a species defined by our refusal to stand still. As we look ahead to Proxima CentauriB, we carry with us the lessons of the past, a legacy of ingenuity, courage, and wonder. This history is not just a story of what we've achieved, but a blueprint for what comes next. Nestled in the Alpha Centauri star system, Proxima Centauri orbits its red dwarf star, Proxima Centauri, at a distance of 4.24 light-years from Earth. Discovered in 2016 by astronomers using the radial velocity method, this exoplanet has become a symbol of hope and curiosity. A potential second Earth that captures the imagination of scientists and dreamers alike. With a mass approximately 1.17 times that of Earth and a position within its star's habitable zone, Proxima Centauri holds the tantalizing possibility of hosting liquid water. But how much do we truly know about this mysterious world, and what makes it so special? Proxima Centauri was discovered through precise measurements of its star's radial velocity. When a planet orbits a star, the gravitational pull of the planet causes the star to wobble slightly. By analyzing shifts in the star's light spectrum, astronomers can infer the presence of an orbiting planet. This groundbreaking discovery demonstrated the power of modern observational techniques. The radial velocity method, along with transit observations and direct imaging, continues to uncover a treasure trove of exoplanets, expanding our understanding of the cosmos. Orbital distance, approximately 0.05 AU, 7.5 million km, from Proxima Centauri, far closer than Mercury is to the Sun. Orbital period, about 11 Earth days. Star type, Proxima Centauri is a red dwarf, smaller and cooler than our Sun. This influences the planet's environment, as red dwarfs often exhibit high levels of stellar activity. Despite its proximity to its star, Proxima Centauri resides in the habitable zone because Proxima Centauri emits far less energy than the Sun. Could Proxima Centauri support life? This question lies at the heart of our fascination with the planet. While the planet's location in the habitable zone is promising, habitability depends on a complex interplay of factors. Does Proxima Centauri have an atmosphere capable of retaining heat and protecting the surface from harmful radiation? Red dwarfs like Proxima Centauri often emit powerful stellar flares, which could strip away a planet's atmosphere over time. If the planet has water, does it exist as liquid on the surface, or is it locked away as ice? Proxima Centauri's close orbit might lead to tidal locking, where one side of the planet always faces the star. This could create extreme temperature gradients, with one hemisphere scorched and the other frozen. A strong magnetic field would be crucial to shielding the planet from stellar radiation. Without it, any existing atmosphere could be eroded over millions of years. If Proxima Centauri harbors life, it would likely differ drastically from life on Earth. The planet's red dwarf star emits primarily infrared light, meaning photosynthetic organisms, if they exist, might absorb light differently than plants on Earth. The discovery of even microbial life would be revolutionary, forcing us to reevaluate our place in the universe. If Proxima Centauri is lifeless, it still serves as a testbed for understanding planetary evolution and the factors that make a world habitable. Proxima Centauri is one of thousands of exoplanets discovered in recent decades. These distant worlds come in a staggering variety of sizes, compositions, and orbits, challenging our understanding of planetary systems. Hot Jupiters, massive gas giants that orbit close to their stars, defying conventional formation models. Super-Earths, rocky planets larger than Earth but smaller than Neptune, representing a new category of worlds. Ocean worlds, planets covered entirely by liquid water, offering intriguing possibilities for alien life. Kepler Space Telescope revolutionized our understanding of exoplanets by discovering over 2,600 confirmed planets. TESS, Transiting Exoplanet Survey Satellite, continues the search for exoplanets around nearby stars. James Webb Space Telescope, JWST, equipped to study exoplanet atmospheres, searching for biosignatures like oxygen, methane, and water vapor. What makes Proxima Centauri stand out is its proximity. At 4.24 light-years, it is tantalizingly close compared to other exoplanets. This relative nearness makes it a prime target for future missions aimed at direct imaging or even interstellar probes. In 2016, the Breakthrough Starshot initiative proposed sending a fleet of tiny, laser-powered spacecraft to Proxima Centauri. Traveling at a fraction of the speed of light, these starships could reach the star system within decades, providing humanity's first close-up view of an exoplanet. If Proxima Centauri proves to be habitable, it could one day host human settlers. Imagine domed cities beneath an alien sky, where pioneers adapt to a new world while gazing back at the distant dot of Earth. Colonization would bring its own challenges, from developing self-sustaining ecosystems to adapting to lower light levels from the red dwarf star. Yet, the dream of living on another planet pushes the boundaries of what humanity can achieve. Are we alone in the universe? What responsibilities do we have to preserve life, both here on Earth and potentially elsewhere? How might discovering another habitable world reshape humanity's sense of purpose? In searching for answers, we find not only knowledge, but a deeper understanding of ourselves. Proxima Centauri is more than a scientific curiosity. It is a symbol of what lies beyond. Whether or not we ever set foot on its surface, the journey to understand it will push the boundaries of human ingenuity. As we stand on the cusp of this interstellar era, Proxima Centauri reminds us that the stars are not just distant lights in the sky. They are destinations waiting to be explored. Traveling to Proxima Centauri poses challenges that dwarf anything humanity has ever attempted. At 4.24 light-years away, it would take the fastest spacecraft built to date, Voyager 1, over 70,000 years to reach it. The vast distances between stars reveal the formidable obstacles of interstellar travel. This section delves into these challenges, examining the technological, logistical, and human barriers that must be overcome to make interstellar travel a reality. The first and most obvious challenge is speed. Current propulsion systems, such as chemical rockets, are inadequate for interstellar distances. They are powerful enough to escape Earth's gravity and reach other planets, but they fall woefully short for interstellar missions. Why current technology falls short? Chemical rockets. Limited by the amount of fuel they can carry and the energy density of chemical reactions, they are too slow for interstellar travel. Ion propulsion, efficient for long-duration missions, but produces low thrust, making it impractical for crossing vast distances quickly. Potential solutions to achieve interstellar speeds, we must explore alternative propulsion systems. Nuclear propulsion. Concepts like nuclear thermal and nuclear fusion rockets could provide higher energy density and longer operational lifespans. Light sails. Propelled by lasers or sunlight, light sails offer a feasible path to achieving significant fractions of the speed of light. Antimatter engines. Harnessing the energy from matter-antimatter annihilation could revolutionize space travel, though this technology remains theoretical. Space is not a benign environment. Outside Earth's protective magnetosphere, cosmic rays and solar radiation pose significant risks to both humans and electronics. Sources of radiation: cosmic rays, high-energy particles originating from distant supernova, stellar radiation. Proxima Centauri, as a red dwarf, emits frequent flares that could bombard spacecraft with lethal radiation. Potential countermeasures: radiation shielding, using dense materials like water or advanced composites to absorb harmful particles. Magnetic fields. creating artificial magnetospheres to deflect radiation, mimicking Earth's natural protection. Interstellar missions will require enormous amounts of energy, both for propulsion and onboard systems. Generating and storing sufficient energy over decades or centuries is a critical hurdle. Power generation options: nuclear reactors. Compact and long-lasting, they could power both propulsion and life support systems. Solar panels. Effective near stars but impractical in deep space where sunlight is weak. Antimatter storage. A futuristic solution with immense energy potential but significant technical challenges. Communicating with a spacecraft traveling to Proxima Centauri is another daunting challenge. At 4.24 light-years, a single message would take over 8 years for a round trip. Challenges of long-distance communication: signal degradation. Weak signals over vast distances require advanced receivers to decode. Latency. Real-time communication is impossible, complicating mission operations. Proposed solutions: high-gain antennas. Boost signal strength for better clarity over long distances. Laser communication offers higher data rates than radio waves but requires precise aiming. Autonomous systems equip spacecraft with AI to make decisions independently, reducing reliance on real-time commands. An interstellar mission would span decades or even centuries, requiring spacecraft to function reliably over immense timescales. Challenges: material degradation. Constant exposure to cosmic radiation and micrometeoroids could damage spacecraft components. System maintenance. Without human intervention, systems must be self-repairing or highly redundant. Self-healing materials. Advanced materials that repair damage autonomously. Redundancy. Multiple backup systems to ensure mission-critical functions. AI and robotics enable spacecraft to diagnose and repair issues independently. Sending humans to Proxima Centauri would magnify the challenges of interstellar travel. Crewed missions require not only life support, but also solutions for physical and psychological health over long durations. Oxygen and water recycling. Closed-loop systems to sustain life without resupply. Food production. Growing food on board to reduce dependency on stored supplies. Bone and muscle loss. Prolonged exposure to microgravity weakens the body. Radiation exposure. Higher doses increase cancer risks and other health issues. Psychological challenges: isolation and confinement. Decades in a spacecraft could lead to mental health issues. Ensuring cooperation and harmony among the crew during long missions. Proposed solutions: artificial gravity. Rotating spacecraft to simulate gravity and mitigate health risks. Psychological support. Virtual reality environments and entertainment to reduce stress and boredom. Interstellar exploration raises profound ethical questions. Resource allocation. Should humanity invest in interstellar travel while problems on Earth persist? Preserve it? Generational missions. If travel requires multiple generations, how do we ensure the well-being of future crews born en route? Addressing these dilemmas requires a balance between ambition, caution, and ethical foresight. The Breakthrough Starshot initiative illustrates how some challenges of interstellar travel might be tackled. The project envisions using powerful lasers to propel tiny spacecraft equipped with cameras and sensors. Speed. Achieving up to 20% the speed of light, the starships could reach Proxima Centauri in about 20 years. Feasibility. Relatively low cost compared to traditional spacecraft. Limitations. Fragility. Miniature spacecraft are vulnerable to damage from micrometeoroids and radiation. Data transmission. Relaying data back to Earth remains a major hurdle. Despite these challenges, Breakthrough Starshot represents a significant step toward realizing humanity's interstellar ambitions. The obstacles to interstellar travel are immense, but not insurmountable. Every challenge, be it propulsion, radiation, or human endurance, offers an opportunity for innovation. As we confront these barriers, we are reminded of humanity's resilience. The journey to Proxima Centauri, they will require the collective ingenuity of scientists, engineers, and dreamers across generations. It is a challenge worthy of our species, one that will redefine what it means to explore. Pushing the boundaries of speed to make interstellar travel a reality, humanity must develop propulsion systems capable of achieving unprecedented velocities. Traveling to Proxima Centauri, even at a fraction of the speed of light, demands a fundamental rethinking of how spacecraft are powered. In this section, we explore cutting-edge concepts and emerging technologies that may one day take us to the stars. The concept light sails rely on the momentum of photons, particles of light, to propel spacecraft. Though photons have no mass, they carry momentum, and when they strike a reflective surface, they impart a small push. Over time, this push can accelerate a spacecraft to significant speeds. Applications in interstellar travel, the Breakthrough Starshot project proposes using powerful Earth-based lasers to propel small spacecraft equipped with light sails. These starships could achieve up to 20% the speed of light and reach Proxima Centauri in approximately 20 years. Challenges precision. The laser must remain focused on the sail across vast distances. Durability. Light sails must withstand intense laser beams and micrometeoroid impacts. Power requirements. Generating sufficient laser energy to propel a spacecraft requires massive infrastructure. The concept nuclear propulsion utilizes the immense energy released by nuclear reactions, either fission or fusion, to propel spacecraft. Two primary approaches are under consideration. Nuclear thermal propulsion, NTP, uses a nuclear reactor to heat propellant, such as hydrogen, which is then expelled to generate thrust. Nuclear fusion propulsion harnesses the energy of fusion reactions, similar to the processes powering stars. Applications in interstellar travel. Nuclear propulsion could achieve higher speeds than chemical rockets, reducing travel times to nearby stars. Fusion-powered spacecraft, though still theoretical, could potentially reach 10 to 20% the speed of light. Challenges technical feasibility. Fusion propulsion requires overcoming significant engineering hurdles, such as sustaining stable fusion reactions. Radiation shielding. Protecting the spacecraft and crew from reactor emissions is critical. The concept antimatter annihilation. The collision of matter and antimatter produces energy with 100% efficiency, making it one of the most potent energy sources known. In an antimatter propulsion system, this energy could be used to generate thrust. Applications in interstellar travel. Antimatter engines could enable spacecraft to reach speeds approaching a significant fraction of the speed of light. They offer unmatched energy density, minimizing the mass of fuel required. Challenges production. Producing and storing antimatter in sufficient quantities is prohibitively expensive with current technology. Containment. Antimatter must be stored in magnetic traps to prevent contact with matter, which would result in annihilation. The concept inspired by Einstein's theory of relativity, warp drives involve bending spacetime itself to achieve faster-than-light travel. The most well-known theoretical model is the Alcubierre drive, which contracts space in front of a spacecraft and expands it behind, allowing the craft to surf through space-time. Applications in interstellar travel. A warp drive could make interstellar travel feasible within human lifetimes, bypassing the limits of conventional propulsion. Challenges exotic matter. The Alcubierre drive requires negative energy or exotic matter, which has not been proven to exist. Energy demands. The energy required to warp spacetime is currently beyond our technological capabilities. The concept ion and plasma propulsion systems expel ionized particles to generate thrust. These systems are highly efficient, requiring less propellant than traditional rockets. Applications in interstellar travel. Ion engines, such as those used on the Dawn spacecraft, are well suited for long-duration missions within the solar system. Advanced versions could serve as auxiliary propulsion for interstellar probes, particularly for course corrections. Challenges low thrust. Ion engines provide steady but weak acceleration, making them unsuitable for rapid travel to distant stars. Solar sails, a variant of light sails, utilize a sun's radiation pressure to propel spacecraft. While less powerful than laser-driven systems, they are simpler and more practical for near-term missions. Breakthrough Starshot's innovations, combining solar sails with laser propulsion, could allow for ultra-light probes to be accelerated to interstellar speeds. The concept envisions thousands of small spacecraft launched toward Proxima Centauri, each equipped with cameras, sensors, and communication devices. Future spacecraft may combine multiple propulsion technologies to optimize performance. Fusion light sail hybrids use nuclear fusion for initial acceleration and light sails for sustained speed. Ion warp hybrids employ ion propulsion for maneuvering and warp technology for interstellar travel. Hybrid systems could offer the flexibility and efficiency needed to tackle the diverse challenges of interstellar missions. Several organizations are actively exploring advanced propulsion concepts. NASA's Innovative Advanced Concepts, NIAC, supports early-stage research into groundbreaking technologies like fusion and antimatter propulsion. The European Space Agency, ESA, investigating nuclear and laser-based propulsion methods for deep space exploration. Private initiatives. Companies like SpaceX and Blue Origin are laying the groundwork for technologies that could one day contribute to interstellar missions. Ethical and environmental considerations. The development of advanced propulsion systems raises ethical questions. Energy use. How do we balance the immense energy demands of interstellar travel with the need to address energy scarcity on Earth? Space debris. High-velocity propulsion systems could create hazardous debris fields in space. Planetary protection. What safeguards will be in place to ensure interstellar missions do not inadvertently contaminate alien ecosystems? The road ahead. Advanced propulsion systems represent the key to unlocking humanity's interstellar future. While many of these technologies remain in the realm of theory, ongoing research is steadily transforming dreams into reality. As we explore these frontiers, the journey itself will redefine the limits of human ingenuity and ambition. The stars are no longer beyond our reach. They are destinations waiting to be claimed. From the moment early humans first ventured out of Africa, our species has been driven by an insatiable curiosity. This desire to explore, to see what lies beyond the horizon, is deeply ingrained in our identity. Interstellar travel represents the next chapter in humanity's journey, a quest to leave the cradle of Earth and find our place among the stars. But interstellar exploration is not just a technological challenge, it is a profoundly human endeavor. It compels us to confront who we are, why we explore, and what it means to venture into the unknown. A deep-rooted instinct exploration has always been a defining trait of humanity. From crossing oceans to reaching the moon, every great leap forward has been fueled by the desire to know and to grow. But why do we feel this compulsion? Survival. In the past, exploration often meant the difference between survival and extinction. New lands offered resources and opportunities. Curiosity. The need to understand our world and the universe beyond drives scientific discovery and innovation. Legacy. Exploration allows us to leave a mark, to ensure that future generations remember our achievements. Proxima Centauri, as a symbol, the journey to Proxima Centauri is about more than reaching another planet. It represents the human spirit's refusal to accept limits. The stars are not just destinations, they are a mirror reflecting our deepest aspirations. A new perspective on humanity, looking at Earth from space, has always offered a humbling perspective. The iconic pale blue dot photograph, taken by Voyager 1, reminds us of our shared fragility and unity. Traveling to another star could similarly redefine how we view ourselves as a species. What does it mean to explore? Interstellar travel raises profound questions about our purpose. Are we explorers by nature, destined to venture into the cosmos? What responsibilities do we carry as we expand beyond Earth? How will discovering new worlds change our understanding of life and existence? Ethical considerations if we discover life on Proxima Centauri b. What obligations do we have to protect it? How do we balance our ambitions with the need to preserve the integrity of alien ecosystems? These questions force us to think beyond ourselves, considering the broader consequences of our actions. Isolation and loneliness, a journey to Proxima Centauri, even at significant fractions of the speed of light, could take decades. For astronauts or settlers, the psychological strain of such isolation would be immense. Strategies for coping: virtual reality, VR, immersive environments could help reduce feelings of isolation by simulating Earth-like settings. Community building, ensuring that crews form strong social bonds, will be critical to maintaining morale. Mental health support, AI-driven counseling systems could provide real-time psychological support. If interstellar travel spans multiple generations, the human element becomes even more complex. A generational mission would involve people born and raised entirely aboard the spacecraft, never knowing Earth. Cultural and social considerations: identity. How would individuals identify with Earth, a planet they have never seen? Education. Ensuring that each generation receives the knowledge needed to continue the mission. Governance. Developing systems to manage resources and resolve conflicts over centuries. Ethical dilemmas: is it fair to ask future generations to inherit a mission they did not choose? How do we ensure that the original purpose of the mission is preserved across generations? The power of wonder at its core, interstellar exploration is driven by wonder, a desire to witness the unimaginable and to answer questions that have lingered for centuries. What would it feel like to stand on the surface of Proxima Centauri, gazing up at a dim red star? Legacy and connection: interstellar travel is not just about reaching new worlds, it's about ensuring that humanity's story continues. By venturing into the cosmos, we connect with something greater than ourselves, forging a legacy that transcends time. A shared goal: the challenges of interstellar travel demand global collaboration. No single nation or organization can undertake such an endeavor alone. Working together to reach Proxima Centauri b could unite humanity in ways that no other goal has achieved. A catalyst for progress, the pursuit of interstellar travel will drive advancements in science, technology, and society. It could inspire generations to dream bigger and strive for a better future, both on Earth and beyond. Proxima Centauri is more than a destination, it is a symbol of humanity's potential. By striving to reach this distant world, we affirm our belief in progress and our capacity to overcome even the greatest challenges. Closing reflection: as we set our sights on the stars, we carry with us the hopes and dreams of countless generations. Interstellar travel is not just about discovering new worlds, it's about discovering what it means to be human. Interstellar travel is humanity's greatest challenge and its greatest opportunity. It represents the culmination of centuries of exploration and innovation, a testament to our enduring curiosity and resilience. Proxima Centauri is more than a distant world, it is a symbol of what we can achieve when we dare to dream. As we close this exploration of interstellar travel, we reflect on the lessons learned, the obstacles overcome, and the incredible potential that lies ahead. A fragile beginning: looking back on Earth from space, we see a small, fragile world suspended in the vastness of the universe. This perspective reminds us of our shared origins and the responsibility we have to preserve our home. Our expanding horizons: Proxima Centauri b, though distant, reminds us that Earth is not the center of the cosmos. The stars beckon us to expand our horizons, not just physically but intellectually and spiritually. A unified effort, the journey to Proxima Centauri b will require the combined efforts of nations, organizations, and individuals. Overcoming the barriers of propulsion, radiation, and human endurance will demand innovation on an unprecedented scale. Lessons from our past history has shown that humanity thrives when faced with great challenges. The Apollo program, the construction of the International Space Station, and the ongoing exploration of Mars have demonstrated our ability to achieve the extraordinary. Interstellar travel will be no different. A vision of the future: imagine a future where humanity is no longer confined to Earth. Generations born under alien skies, gazing at their distant ancestral home, will carry forward the legacy of exploration. Proxima Centauri could become the first step in humanity's transition to a multi-planetary species. The ripple effect, the technologies and discoveries developed for interstellar travel will have profound impacts on life here on Earth. Clean energy, advanced materials, and AI-driven systems are just a few of the innovations that could emerge from this pursuit. The meaning of exploration: why do we strive to reach the stars? Perhaps it is because exploration defines us. It is a way to seek meaning, to find our place in the universe. By reaching for Proxima Centauri we affirm that humanity's potential is limitless. A hopeful legacy, the journey to another star will not only leave a scientific legacy, but also an emotional and philosophical one. It will inspire generations to think beyond their immediate surroundings, to dream of the infinite. Proxima Centauri b, a new beginning. Proxima Centauri is more than a distant planet. It is a beacon of possibility. It challenges us to innovate, to collaborate, and to reflect on our shared humanity. It reminds us that the stars are not beyond our reach. They are destinations waiting to be explored. A call to action as we stand on the cusp of this interstellar era. The question is no longer if we will journey to the stars, but when. The pursuit of this dream will define humanity's legacy for millennia to come. The final question: what if our destiny lies not on Earth, but among the stars? This question, profound and inspiring, will guide humanity as we embark on the greatest journey of all. The dream of interstellar travel is more than a technological challenge. It is a testament to humanity's boundless spirit. Proxima Centauri represents a future where we are not confined by our limitations, but defined by our aspirations. The stars await. Will we answer their call? Thank you so much for watching this video. I truly appreciate your time and attention. If you enjoyed this journey, don't forget to hit that like button and subscribe to the channel for more exciting content. Your support means the world to me and helps me create even more amazing videos for you. Stay tuned, and I'll see you in the next one.